Alrighty, folks. Hopefully everybody is doing well. We are going to jump into module number 21, so hope you had a good weekend there. Just on the logistics, assignment 8 is out on splines, and it's a fun one. It shouldn't be too stressful. I've provided a lot of the stress code, and I'll talk about that and show that in a moment, but let's go ahead and dive into module number 21 and talk about concurrency here, okay? So I have the slides ready, and as always, make sure you complete the in-class activity. All right, so just diving into the slides here, let's take a look. A little pre-class warm-up since we've been talking about splines and also talking about the Boost library. One of the neat things is, as I mentioned, is this Boost library really has lots of different C++ libraries built in and functionality. So it even has one built in for splines. So anytime you think you need something, it's probably in this Boost library. This will be another candidate for the advanced topics in the last week, which are sort of auxiliary topics, not things we're going to have time to build assignments off of, but otherwise might be worth looking at just for your future C++ career and just to know what exists. So maybe setting up and using some of the different Boost libraries. So I'll be listening to folks in office hours and just doing a little bit of my own planning there just to decide what some of those topics will be. But I think Boost would be a nice one. But anyway, just wanted to show that off to you and just show that, C++ really is a batteries included language. We like to think of other languages that you might have used like Python and so on as also languages that have lots of libraries, but C++ is no different. Okay, so we're obviously recording, and last time what we talked about were different animation techniques. So we're getting into this point where we're making our pixels or at least we started with our pixels and how to just manipulate them, put them on the screen, change the colors and so on. Then we got into curves, and then we got into making them move a little bit with some of these techniques. So we talked about a cool one called color cycling, and then we looked at just traditional sprite animation. So a lot of live coding on that one, just how to sort of split up an image and think about how to do that. Now, the sprite animation itself, while a cool thing and important for things like games, graphics, websites, and so on, is not enough on its own. It was also a nice application of, well, when you're working with a lot of data, you want to be a little bit more conscientious of how you're spending those resources. So we actually built a little resource manager as part of that exercise. And this is your first design pattern in C++. It's something called the singleton. So it's where you say, hey, I only want exactly one class, and that class is going to manage some resources. So it gives you a sort of global variable is a way to think of it, but just one place where you're managing resources. In this case, we showed how it could be useful for managing images and making sure that they're only loaded once. So it's a common design pattern. There's pros and cons to it. It's sort of easy to use, but on the con side, it's globally accessible, and you may or may not want that. But the other point of this exercise was also to show you how to use static in a class and show that static members are shared amongst all instances of a class. So just looking into the another use case of static, again, just sort of understanding how that keyword works when creating programs in C++. All right, so on the logistics side, otherwise A8 on splines is out. And as mentioned, it should be a relatively short assignment. For this one, I've decided to present some more source code because we did a live code of it in the previous module. So, folks have been following along and hopefully coding along the examples that have been coding. So you have a lot of the implementation. So the really sort of interesting part, and here's an example of what you can create, is just sort of understanding the structure of this code, getting used to doing some more math type of applications in C++. This is a nice one to sort of start with. So you're actually going to be given a lot of this sort of spline resources, but I think what's really interesting, so you're not going to be too challenged as far as the coding part. I mean, this is all you really need to implement in the right place, but really the understanding and taking an idea and implementing it. And I think that's part of the cool exercise here, or at least what I want folks to take away to be. You're going to have to do a little bit of other work with just building and refactoring a piece of code that you didn't necessarily write. You can use, you can refactor your implementation if you like. But that's another exercise that we haven't really done in C++ yet, sort of refactoring code. So in this case, it's just going to be building your own HPP and CPP files, so just taking the code, refactoring it into its own files, making sure it compiles and runs, okay? So really nice video as well, talking about splines and to help give you the intuition, but I've tried to comment the code otherwise for us to learn from, okay? And then there's a little bit of reading on some other things with the code. So again, sort of intentionally, you're going to see some new C++ stuff when you read through the code in our refactoring. Default being a particular one that I want you to pay attention to and read about. Okay, so that's going to be what's it for the assignment. For folks, I think it's a good one. Should be pretty manageable time-wise. But hopefully, high impact on your learning. All right. So it's good to have some of those assignments mixed in as we finish up the semester here. All right. So for today's topic, though, we're going to do a little bit of a architecture review. Okay. So a long time ago, when computers were created, we really, and in the way that we've been programming in this course as well, we've really written software with this idea in mind, where we have some instruction, we write a line of code and then we execute it. Then we have another instruction, a line of code, then we execute it. And it's very sequential how we're doing this execution, just one line of code after the other. And for a long time, our computers only actually had one CPU core, so one brain that could sort of do the thinking and processing of these instructions, one after the other. So this sort of made sense that this is how we thought about computation, and this is how computers ran. And we could sort of abstract this visualization further, right? Just thinking about the C++ programs we've been writing, where we have a main function, and then it calls foo, foo calls bar, and then bar within it, calls baz, and we just sort of have this execution here, one function after the other here. Maybe a function calls another function, but it doesn't really matter. It's just sort of one sequential flow here, control flow of how our program is running. Now today, though, we can have multiple sort of streams of execution here. So you'll notice here we always have one entry point, but while we're executing foo, bar, and baz here, our computers today have multiple CPUs. So we can have foo, bar, and baz also executing on a different core on our machine. So typically machines that you buy today have dual core or quad core, and I'm going to show some example fun machines too, just to show that there's multiple CPUs so you can do multiple things at once. And the reason for this is, or why we have more cores today, has to do with what's called Moore's Law. So for folks who have taken a systems class, this will be familiar. For folks who haven't, I want to introduce this to you, but way back in 1965, Gordon Moore predicted the number of transistors would roughly double every 18 to 24 months. The transistor is the thing on your machine that turns on and off essentially and is doing the computation. So over time here, as we're going on time on the x-axis, we're getting more of these transistors. More transistors means we can do more processing. So every 18 to 24 months, so every 2 years if you want to think of it, we were getting twice as much power just by the technological innovations, essentially shrinking our transistors and fitting more of them onto our chips so we could do more processing. But the problem is, and this is especially true as we reach, today, 2020, 2021, and so on, as the processors, the transistors, get closer and closer, more heat is generated because you're packing things much more tightly together, right? Imagine, putting one person in an elevator versus if you've ever been in a packed elevator before, it's, more heat's going to be generated. There's more people, more things going on. Same in computers. More transistors, the transistor density increases, and the heat becomes a problem. The CPU can actually melt. Okay. Now as our CPUs are actually getting faster too, we call that the clock speed, they demand more power. And that's another problem. So we have a lot of power being demanded in a very tight space, and that's what causes the sort of heat increase, increased energy consumption, and so on. And then the other issue is, we can compute things very fast, but memory, our ability to access data that's stored on our in our memory, whether it's from your hard drive, your RAM, or somewhere in your machine, just wasn't able to keep up with the speed at which we were able to compute things. Okay, so this is what's known as the processor gap. This next figure here. So over time here on the x-axis, the performance as we go up increases. So our processors were getting faster, but our ability to access things from memory, so storage in our machines, meaning a hard drive or a RAM or something else, some other type of medium, isn't as increasing as fast. So you can see here over 30 years, we've had about a 10x increase in memory. Not bad, but not great compared to our processors, which over 30 years have increased, more than 10,000 times faster. Okay, so we say our applications are thus I/O bound, meaning we're often waiting when our processors are executing to fetch information from storage, from our hard drives, to actually do the computation. Okay, so now we try to mitigate this problem in a relatively simple way from a hardware perspective by having more cores on our machine and just splitting things up in parallel. Okay, so I'll show a few examples. I like using gaming consoles because they're kind of fun and an obvious application where you want to increase performance, but the same thing's true on your computer. But basically, you have multiple slower cores placed on your CPU, and you can actually see some of these here. This is a quad core, so I have a set of 4, 1, 2, 3, 4 cores here, and then 1, 2, 3, and 4. And since we have more cores on our machine, then we can do more computation, okay? And we can separate out that computation, so essentially keeping one of the cores busy. Again, this is the same idea as if I gave you a homework assignment and you split it into 8 pieces for 8 different people to work on. It doesn't matter how, if one person's, twice as slow at completing the assignment, it wouldn't matter because you've split it up into 8 smaller chunks. So by the end of the day, you'll finish it faster if you can divide up that work. Okay, so that's the idea with our CPUs. Okay, so our ability thus to increase or utilize these CPUs, though, however, means we need to think about when we program, how do we divide up our work and do what's known as concurrent or parallel programming. Okay. And just for fun, here's some other console specs just to see the trend. The newer Xbox has 8 cores on it. The Xbox Series X also has 8 cores. They're running a little bit faster than the other ones. So they were at 1.75 gigahertz. The new Xbox is about twice as fast, almost a little bit more than that with 8 cores. PlayStation 5, same deal here, 8 cores. Even portable devices, your Vita for the PlayStation had 4 cores. Most of your cell phones have 4 cores in them, probably 2 to 4 cores, depending on what you own, an Android or Apple or maybe a BlackBerry device. But that's the idea. And most of your machines that you own, your desktop or laptops, are probably quad core, 8 core. You might have more. In fact, if you're on Linux and want to do the experiment, you can do ls for listing stuff, but ls CPU, and it'll usually tell you how many cores you have. So my machine here has 16 here. So that means I can break things roughly into 16 tasks pretty easily. We're going to talk about what threads mean in a moment. So you can take how many cores you have and how many threads per core, and that's roughly how much you can divide your work. So about 32 threads is about what I have on my machine here. Okay, but this general trend in architecture, in order to get more concurrency and more parallelism, that is the ability to do more things at once, has been going on a long time. It's just been at the sort of supercomputing level. So way back in 1964, the Cray machine here actually had multiple processors on it, right? That's how these supercomputers break all these speed records and process so much data. If you've seen complex bioinformatics or computational chemistry simulations, they're running on these machines that are very, very parallel, and that's why they're able to compute so much. Fun story here, why these machines, you might be wondering, had couches on them. It's because allegedly, one, it was a way to sort of easily, these flipped up and you had the panels to the machine to access different components. But famously, also, the engineers like to sleep on these couches if they were working late and they got nice and warm from the machine, and they would just fall asleep on them. So that's why they have the couch there. Kind of interesting. Very pragmatic. But regardless of this, idea, the trend is here to stay. It's not a new or an old idea, so we have to realize that we want to be able to program and take advantage of all these cores on our machine, on our expensive hardware. We've been doing lots of tasks with pixels, for example, in this course, and it might make sense that we could operate on multiple pixels at once. Okay, so let's talk a little bit about concurrency and parallelism, this idea. We're going to be talking about threads and primarily about concurrent programming. Now, there is a difference between when I say something's concurrent and parallel. Some of you will take a systems or maybe a concurrency or parallelism class and further learn about this, but the idea is concurrent programming is you can have multiple things happening at once, but there is some order. Whereas parallel means you have truly two things at any instance can happen at once. So the distinguishment is sort of two queues of people here lining up to get coffee. So two pairs of people are able to line up here. So that's what's going on concurrently, but only one person can access this shared resource here, the coffee machine. Versus if you want to do things truly in parallel, you would have two coffee machines and have two people able to access it at once. Okay, so there's a difference. We're going to be focusing on concurrency today. So if you have two CPU cores, if you want to think about the coffee machine as a CPU core, you could, have 4 lines of people all queued up to access these coffee machines. So for example, let me go ahead and just launch our drawing program just so I can draw that example. And let's see. So we can still, concurrency isn't necessarily inherently slower, but we could have 2 coffee machines here. Right, here's your cups of coffee here. And we could have people lining up here, but still in 2 queues, able to access the 2 coffee machines here, okay? So that is the concurrency. Okay, so we can still always scale up in this way and make things faster. We can line up people more efficiently or in 2 lines. Maybe they have to do something else like, the person when they reach this point has to get their wallet ready or whatever. So you still get some sort of speed up here, even though the shared resource or the sort of bottleneck is right here. Okay. Anyway, we'll talk a little bit more about this in a moment. But the main mechanism for achieving this, which is our topic of today, is what's known as a thread. Okay, so a thread is what's going to allow us to execute 2 control flows at the same time. So you're going to have your main thread, which we've been programming in. We haven't had to think about it, but it's really the main thread of execution, where we're executing one function at a time, one after the other. But now we'll be able to create new threads programmatically that have their own logical control flow, where you can have a function, call another function, and a function, and it's doing its totally own thing over here. Okay, you could have 1 thread, you could have 32, you could have 100. It doesn't really matter how many you have, but we're now going to have the ability to do things concurrently. Okay, so again, concurrency is going to be our ability to have multiple control flows, and they're going to share the data in our program. Now, this is one of the sort of important distinguishments to keep in mind, that we have these multiple control flows, but they're actually sharing all of the data or most of the data on our programs. The threads have their own sort of local data, but otherwise, if I have some global data structure, say some array, I can share or access the information in that array from multiple threads. Okay, so one way to think about that, let's think about our image processing assignment here. Let's say we had our image here, or rather, let me just draw our image. And if I want, I could divide up my pixels into 4 quadrants and have different threads acting on pixels, but just within their region, just within their boundary, okay? So this is one way that we can have multiple threads, and they share this data, all of our pixels in the image, okay? So they're able to if we're doing the grayscale filter or whatever it may be, change what these pixels are here. Okay, so that's the idea. Okay, and we're gonna maybe talk a little bit about parallelism in the course, but there's other mechanisms. I'm gonna mention one later at which we can do things simultaneously. Okay, um, so we need specific sort of ways to access our hardware to do this. For the most part, threads are a little bit more more available to us to think about. But if we want to do something parallel, like using our graphics card, for instance, to do a parallel task, we're going to need to learn some other software and API and toolkits to do that. So for folks who want to join me in graphics, we'll do a lot of that, or in systems, we'll do some parallel work as well. Okay, now one area where we do get some parallelism, just to talk about it a little bit, is whenever you're actually executing an instruction, and this is a bit of an aside here, the instruction here is getting ready to run, and then you actually fetch that instruction, but your CPU has to go through this process of decoding what that instruction is, then executing it, and then writing any changes to memory, storing a result, if you do an add operation, for instance. And then, your second instruction starts and you have to fetch and figure out, well, what is that instruction? Are you adding something, subtracting something, whatever it is? You decode it, you perform the actual thing, and then you write the result. But you can actually parallelize this, meaning while you're fetching your first instruction, you can start decoding it. And then while you're decoding your first instruction, you can start fetching another instruction. So this is some parallelism that you get, or that's taking place in your CPUs for free. So there is parallelism going on already in our programs. It's just a little bit hidden from us. I call it implicit because it's just given to us for free. Our compilers might help us with this sometimes. Our CPUs usually handle this otherwise. Okay, and this is called pipelining. Okay. Now we do have, and again, this is a little bit of a brief aside, but then we have the other types of parallelism where you as a programmer are going to create that parallelism. So maybe you're using your GPU, and CUDA is one of the tools that I wanted to mention that exists, or OpenCL. So folks who are in data science, you might look at some of these tools eventually for machine learning projects, for instance. Other folks might look at this for graphics or game programming, just ways to do things in parallel and thus improve performance, okay? On our CPUs, there's also something called single instruction multiple data, where we can apply one instruction here, and that's what this diagram is showing. You have one instruction, and it gets applied to a bunch of pieces of data. Okay, single instruction multiple data, okay? These are called SSE or AVX instructions. This is more than you need to know, but this is a toolkit for that you would again see with me in systems, or perhaps other folks who take any parallelism courses on how to speed up your programming by executing the same instruction on multiple pieces of data. So that's how you get some parallelism. Okay. So there's lots of examples of other parallelism here. I just want to sort of give you a teaser and get you excited about it. Anything gaming, anything machine learning, anyone, a lot of you folks who are going to go off and do data science stuff are going to be able to use parallelism. So you can take a look at some of these things. I have some graphics examples, or if you search machine learning, parallel programming, anywhere that, or any domain that you need to increase performance, which I would argue is almost everywhere, you're going to see parallelism as well as concurrency. Okay, so that's the main motivator. That's why we're going to learn about threads a little bit in C++ today. This ability to increase performance by doing multiple things at once. Okay, and sometimes it's also just necessary to be able to have programs that work concurrently, where multiple things are happening at once, because, well, that's how our world works. If you think about an orchestra, for example, there's an ordering, there's multiple instruments playing at once, and sometimes they stop, or traffic lights, right? For anybody who drives in Boston, you know how important these are, right? The ability to allow, two sections, of the road to, cross while the other folks at the intersection wait. So that's just the idea. And also just thinking about programs concurrently, it can help us structure our programs and break our work into smaller chunks. And we will do that as part of a homework here. So this is a teaser. Okay, so what is our tool? Our tool is a thread. It's otherwise known as a lightweight process. And okay, so again, let's just take a look here for a second. Again, threads, lightweight process. So this is what they look like from a sort of systemsy perspective. Again, not super important today. We're just going to want to know how threads work. But again, just to capture this idea that when you have one program running, one process, your application, the game, graphics application, whatever, it has, it's one process, but that process can have many threads of execution doing many things at once, okay? Each thread shares the same data, the same code, data, the kernel context, meaning your operating system switching between processes very fast. If you have multiple applications running, so for example, I have 3 applications here, and the operating system's just flipping between them very quickly as I hover over them and giving them sort of control. You can think of it like that. But what you're going to be able to do is create a thread, and it's going to have its own ID, its own logical control flow, and it has its own local variables, okay? But otherwise, it shares all the other libraries that you've loaded, all the other code, everything, all the global data, and so on, okay? Now, there comes a problem, though, with threads, because if we're sharing all the data, then we can have what's called a data race. That means if 2 threads write to the same location at the same time, it becomes non-deterministic who gets to write there. So let me go ahead and just draw this as an example for you. And I'll just illustrate it with sort of a classic example here. And I'm actually going to give you a non-programmer example here where, let's say this is your refrigerator here, and you open up the door, and inside of your fridge, you look in and it's completely empty. Okay, so there's nothing in here. So you decide that you're going to go off to the store somewhere. So you sort of zoom off in that direction. And then while that's taking place, someone else comes in here and they decide that they look in the fridge and they see that it's empty and there's nothing there. So they also decide that they're going to zoom off to the store. Okay? So what happens though is when you come back, you populate, some groceries in the fridge here. And then your roommate or whoever also comes back and they populate, some groceries here. And maybe you bought the same thing twice here, okay? Because the state of the fridge when you looked at it was that it was empty and you needed some groceries. But now you've got twice as much as you need. Maybe that's a problem, maybe not. It just depends on what you care about. But the idea here is that we need to be able to protect this shared resource here, that's the refrigerator, and be able to have a sort of consistent state, okay? And that's what's known as the data race. Depending on the order that people looked into the fridge or the order that they came back. So for example, if you had gone to the store and came back really quick before your roommate looked, they would have said, oh, it's already full of groceries. I don't need to run to the store. I don't need to do that, okay? So let me give you, that's the sort of real world example, but let me give the other example that we've been using here, and I'll use it with our figure here, where let's say you have 2 threads and they're modifying one of the pixels here, okay? So thread 1 and thread 2. And thread 1, every time it draws to this location, it colors it red. Thread 2, every time it colors it a black pixel here. So depending on the order that these threads execute, which is completely non-deterministic, your operating system chooses when thread 1 and thread 2 execute. You're either going to get a black pixel or you're going to get a red pixel. Okay, so that's the idea. And you might want some ordering to be enforced. Okay, so we have a tool for that. It's called a lock. We're going to show it here. Here's an example where if you have some shared variable here, this one's just called accumulator, you can put a lock around it, and then only one thread at a time can access this value. Now you lose a little bit of your parallelism, but you avoid this problem of a data race, okay? So lock is going to be our tool. I'll show you also how to use that with threads today. Okay, now these problems can get a little bit worse with threads. So for example, the issue is, or the second issue with threads is also called deadlock. So if you use one of these locks, you have to remember when you lock something that when you're done accessing a shared resource, you unlock it. Okay, so let me go. If you prefer the fridge example here, we'll just draw another fridge here. And here's the door open. Here's your shelf. You've got some stuff in here or whatever. Now, if you go here and we use this idea of a lock here, and you take the key here to the fridge with you, but you never return. This is sort of a grim story, I guess. And your roommate comes and looks at the fridge, and the door is closed because they need this key to open it. They will never be able to open the fridge here. Okay, so it's kind of a silly example, but that's the idea of a deadlock. Never returning the key that allows you to access a resource. So it's nice to sort of think of it in a real world way. I'll create one on purpose so you can see what happens. But basically, it's when you lock and forget to unlock your code. Okay. All right. So just a few common patterns that we use with concurrent programming, and this is more of just so you're aware of them. So when you go on to systems and start applying some of your C++, you'll have these keywords in mind. We're going to just start with the basics today, but there's this idea, this problem of what's called a multiple readers, where you can have some piece of data here, data A, and you can have multiple threads reading data A. Okay, so you see the little tick marks here, implying that this thread or this process is reading from data A. Maybe you're transforming, you're just reading from the data and then generating a new piece of data from data A here. Okay, and you can do that safely because you're just reading. You're not actually changing the state of data A here. The opposite of that idea is where you have multiple threads here that are taking in data A and data B, forming some transformation, and then creating some new piece of data. Okay, so you can have multiple threads writing or creating new pieces of data into some greater, composition. Maybe this is like an image processing task where you have two threads writing to the same piece of data here. Okay. Okay, and then since we're writing to the same piece of data, again, we need some locking mechanism for that. Okay, and then you can also have multiple readers and writers, which takes a little bit more coordination. But again, the idea is you just have some shared piece of data here in the middle that you're trying to access. So maybe you're trying to read from that data and then write some new information out. Okay, and again, you can kind of think of this like if you've ever booked a flight for travel, for instance. You have multiple people looking at what flights are available, and then multiple people booking flights that are available. Okay, so you have some lock around this shared data. And then you have to update it every time someone books a flight here or writes out some new data saying, hey, they purchased a ticket. So we have to change what the state is of the thing that everyone's looking at. Okay, so that's just some idea of what that pattern is. So let's go ahead and just look at threads in modern C++. That's what we care about learning here for now. And again, these libraries like Boost, and there's another one by Intel, or again, some folks have taken systems in this class have seen pthreads. Those libraries contain threads, but in modern C++, we actually have them built in, okay? And it's just called the thread library, okay? So that's what we're gonna be looking at, and we get this primitive here, the thread here. Okay, we get a whole bunch of other things like the locks here, the mutexes, and that's what I'm going to walk us through some examples here shortly. Okay, but before I do that, go ahead and give yourself a little break if you need it, and then we will continue. All right, so you've given yourself a little bit of a break here. Let's continue on and look at our first example here, okay? So the new concept here I want to show is just how to launch a thread here. Okay, so here's the example. Here's our main function. You're going to see thread here, which is our new primitive. It's part of the standard library here. And we include the thread library here. Okay, and what thread does when we create it, part of its instructor is it takes the address of a function here. So you have the ampersand here, address of this function here, test, and then any arguments here, which is just 100 and then the parameter here. And it says hello from our thread, and then it prints whatever the argument is that we passed here. And this is executing in a separate thread of execution here, okay? And what it's actually doing then is your program's concurrently running main, so it's going to start executing down here, while in another thread, this portion of the program is running here, okay? So essentially what we call this is a fork join parallelism when we're executing a thread. So we're executing down this path, we have our main function, but we also created that thread here, and it starts to execute. And it'll execute until we specifically say, hey, my thread.join here, which joins this thread that we created, which basically, it's a little bit of a weird term. If you want to think of it like wait, you can, but it basically says, hey, main thread of execution, wait until this thing finishes. If you do other stuff in between, that's fine, but otherwise, don't proceed any further until you finish executing this thread. And this thread terminates or finishes once this function is complete. Okay, so that's the idea. Okay, so let me go ahead and let's just live code this just to create it and show you how to create a threaded program here. So we're going to need to, let's include our standard out library and then our new library, which is for thread here. Okay, and then we just need some test function. Test function where we'll call our thread, where we'll, let's see, create a new thread, okay? I'm just gonna call this test, and you can pass in an argument. You can pass in as many as you want, and I'll just pass in one argument that way. Okay, and we're going to print out a message, hello from our thread. I'm gonna separate this over a few lines. Argument pass to thread is, and we'll just print out that X just to show you that that is what's being printed out here. Okay, so that's going to be our test function. And now let's actually create a thread. So it's part of the standard library. We'll create our thread, and I'll just call it my thread. And again, the address of the function that we want to call here, that's why we have the ampersand. So we're passing in a, again, this is a function pointer coming in here. And this is for this particular function here. And then whatever value we want for the argument for x here. And we can have, if we have more arguments, we just add other parameters here, okay? Okay, so at this point, we create a new thread and pass in a value for its first parameter, okay? And then we wait, so we join with the main thread, which is the same as saying, hey, wait until the main thread finishes executing. Okay, that's the idea here. Okay, so my thread join here. So it's going to join with the thread it was called from, okay, which in this case is main, is the main thread, just to be super explicit about it, okay? And then at the end, once we've joined, then we are back in our main thread. Hello from the main thread. Okay, so let's go ahead and let's just try to compile this and see if it works here. So I'm going to grab, I'm going to just compile this how we normally do. And we're using C++17. This program's called thread, and I'll just output it as prog. And you're going to notice we actually get an error if we just try to compile this. It's going to say, hey, this function here, thread, we don't know about it. It's an undefined reference to creating a thread. Okay, it doesn't know how to do this creation. Well, the trick is we actually have to link in a library, which is, if you're on Linux or for most systems, it's just going to be the pthread. Okay, this was a linker error because we're using this new functionality, but it says, hey, we don't actually know how to, we don't have the code available, the implementation to create a thread. That's hidden in the library. So when I compile it by linking in the pthread library, then it will properly compile. Okay, and now I can run this program. And I'll say hello from our thread. This executes. The argument passed to our thread is 100, and then hello from our main thread. Okay, so that's your first thread example. And I'll go ahead and update this one in the slides so you can practice directly from it. All right, and as always, these examples are also in our GitHub repository if you need. All right, so let's look at another example because I sort of had this warning about what could happen if we access shared data. So in this example, I want to push our thread example just a little bit further and have multiple threads working in our program. Okay, so let me go ahead and just live code this, and then we will discuss what's going on. Okay, so in this example, what I want to do is create multiple threads. And what I'm going to do is create some function here. Let's just call it, well, let's just start with creating the threads here. So how do we create multiple threads? Well, I'm going to use a vector to do this, and it's going to be a vector of the actual thread. I'm just going to call it threads here. So we need to include our vector library, okay? So this will hold our threads, okay? And we can, because threads are some sort of data structure like anything else, this is how we can create multiple of them, okay? So what are we going to do? Well, let's do a loop here. And let's just loop through, oh, I don't know, however many threads we want here. I'm just going to call it the thread count. And let's actually define something here. Define the thread count as, how about 100 here? Let's go crazy and launch 100 threads. Okay, and what I want to do then is start creating all of my threads. And as soon as these threads are created, so I'm going to push back into this data structure a new thread that I create. And it needs to call some sort of function here, okay? And let's go ahead and define this function as just something simple, like an add function. Okay, so the goal of this program is just going to be have a bunch of threads that increment some shared value. Okay, so let's go ahead and create some shared value here. G accumulation shared value acted on by multiple threads. Okay, so that's going to be the idea here. Okay, and all the add function is going to do is just add whatever this x value is that we pass into it, okay? And we can just make it something simple like 1, which is fine. Okay, so we're going to add and then 1. Okay, so we're going to spawn a bunch of threads, 100 of them, and then add them all to this value here. And we should initialize this to a value here. Let's just do a value of 0. Okay. And let's go ahead and just try to run this much and see what happens. Okay, so we need to compile our program and also link in the thread library here. Okay, so if we run our program, it gives us some crazy message here. It says terminate called without an active exception. Okay, so something really weird happened. Well, recall we forgot to join our threads. Now we have to join all of our threads because what's happening here is while we create these threads and are executing this add function, our main program has actually also continued on and it's essentially terminated. So we have threads which are trying to add while our main program has terminated. So that's why we get this sort of weird error here. So what we have to do instead is make sure that we also join all of our threads. Okay, and I'm going to introduce a way to do this that's a little bit new for us because I want to keep teaching us new C++ things as we go. This loop is going to join all the threads. And we haven't talked about this in a long, long time, not since probably the first lecture where I remember explicitly calling out, but this idea of auto, which will automatically deduce the type here of whatever our thread is. So this type of for loop here is a ranged, a sort of for each loop, okay? And this loop will look through all of our threads, and we refer to them as th, okay? So this is the same thing as doing a loop here. We could do for int I equals 0, while I is less than threads.size, I++, and then just sort of access threads at index I join, but this is another sort of clean way to do it. In auto, will automatically figure out the type that this is indeed just a standard thread here, refer to it as a thread. We want the reference because we want the actual thing here. So that's what we are doing in our for loop here. Okay, so let's try this much so far. Let's see if we get rid of that weird error here. Okay, so it compiles, which is good, and no error. Okay, so that's good. So let's see what the work is that we've actually done though. Okay, so let's print out what G accumulation is. And let me just do this here. Okay, and I'll put a little M line. Okay, and then I'll resave, recompile, and rerun. And it's 100. Oh, but I ran it again very quick, and it's only 96. 99, 100. Well, let's see if my math is right, and I keep running it. Most of the time it's right, but sometimes it's not, which is a little bit worrisome. Let's see. So if I have 100 threads, and each time I execute them, they're adding to this global variable 1, it should be 100, but this is exactly what the data race is. So sometimes in our program, so if you remember our little analogies here with the fridge and so on, what's happening is our threads are accessing the same value at the same time. So it's reading in our accumulation value. I'm just going to abbreviate it accum. And thread, let's say 27 and thread 28 of our 100 read it, and they both read it in as 27 here, okay? Because it just happens to be at the same time when they're accessing this shared piece of data, they see that the value is 27. Meanwhile, this thread's incrementing it +1 to 28, and this one's also incrementing it +1, so it ends at 28. So we're actually missing some of the interleaved operations here. Okay, so that's the idea with the thread. So when we have some data that's shared, we need to use a lock around it. Okay, so how do we fix this? Well, we need a lock, and that's called a mutex. So this will allow only one thread at a time to access this value here. Okay, so we'll create a mutex, and usually we create these globally. And I'm just going to name it G accumulation mutex. Okay, that's kind of a big name here. But how we use it is we just say G accumulation mutex, and we lock. Okay, and sometimes I like to indent this here. And then I'm going to do the same thing, but unlock. Accumulation mutex unlock. Okay. Oops. Okay, now if I run this program, I'll recompile it, and I'll rerun it. It should be 100 every single time here. Okay, no problems. Because every time we're accessing this shared value, we have a lock, and only one thread can hold the lock at a time. It's like having one key into somebody's house that has to be shared, okay? So that's the second example here with using threads and with shared data. Now I said I'd also show an example where I forget to unlock. And this is where we run into the deadlock situation. So the first thread's going to race in, grab the key, increment the value, and then they're just going to leave and terminate with the key. So since they terminate into the ether, they never return the key, and our program never finishes. It's just going to wait here forever. So I'll hit Control-C and then reclaim it. So that would be an example of a deadlock for us. Okay. Okay, so here's our example here. Now, you might say, I'm going to forget to use the locks, and maybe it's too complicated, or have all these locks, and it's just a simple integer. Well, there's actually a nice built-in thing into C++ called an atomic. Okay, in atomics, you can think of like atoms. They're indivisible operations, so that means you can't split them up in any way. And if you create your data type with this atomic type, for your accumulator, you actually don't need to use any locks. It's a property of this data structure that's essentially just wrapped a lock inside of it, and it says that only one thread at a time can access this variable, okay? So I actually already wrote a version of this, which I'll update in the slides here, to show you the atomic here. Okay, so here's our accumulation. So there's no locks here, but if I go ahead and rerun this program, so thread 3, you'll see that it gets the same result every time. So it's doing the same thing, launching 100 threads, joining them with the main thread. So that means the main thread waits until we terminate, and then we're just accumulating the value here, whatever x is, from all of our threads. And since we're just adding 1, we expect it to be 100, and this works. So this is another really nice feature of C++, this idea of an atomic. So we don't have to worry about doing anything fancy here. Just does the lock for us. Okay, so here's that example here, so you can take a look. The design, as I mentioned, if you wanted to use this or utilize it, you might, again, just wrap one of these atomic types and maybe just write an increment function, decrement, or a get, and then you can return the actual value. And there's actually a little secret to these atomics. I said that you could imagine having a class and sort of wrapping a lock around it. Atomics actually don't use any notion of a lock here, okay? So they have this is a pretty deep systems concept, but you can actually write lock-free data structures, okay? So just something to get you kind of interesting, because there is a little bit of a cost to locking and unlocking, right? If you think about any time you come home and have to lock your door, that takes some time, but there's actually ways to build these data structures to utilize hardware that's lock-free. So just a little teaser there of something interesting. All right, but let's carry on with some other examples. And in this one, I want to talk a little bit about something called a lambda function, which comes in handy with threads. So let me go ahead and set up a fourth example here. So in this example, I want to teach you a few things rather about the threading library. This idea of what's called a conditional variable, and then a nice way to use it with something called a lambda function, okay? So I'm going to start off by just creating the conditional variable here. And it's just conditional variable, okay? And it's global, so conditional variable. And I need to include not the atomic library, but the conditional variable library, okay? I'm also going to include a mutex in this example as well, okay? Okay, so what we want to do here in this example is let's just create some thread, really two threads, one that's going to report a result and one that's going to change the value of something in our program. So let's just create some value. Okay, I'm going to start setting up something called a conditional variable, which basically means if something has changed or the state of our variable, we're going to create something called a conditional variable. That's this guy. That we want to notify another thread that happens. So we're going to need some Boolean to store that result here. Okay. Okay. So what I'm going to do is create two threads. One's going to be called the reporter, and one's going to be called the assigner. Okay. And it's not super important what these are. All you need to know is that the assigner is going to change the value, and then it's going to say, hey, this happened. The variable was changed. So it's going to update this flag here. And then the reporting thread is going to then execute as soon as it says, hey, the value's changed, and it should be notified, okay? So you'll notice the order is backwards here. And how they're actually going to execute. This thread's going to execute, and then this reporter is. So we could write a function up here for handling the logic of that, but we can actually just put a function within our thread. Because remember, a thread needs to take a function as a parameter, but I'm actually just going to write the function inside of that argument. To do this, we do so with what's called a lambda value. Okay, or a lambda function. So this will be your first lambda function. We'll talk about them a little bit more later, but the idea is there's no name here, no name to the function. It just square brackets. And you put an ampersand in between, which is what's called the capture, which says anything that happens in this function, such as if I access this value here, it's going to actually change that value. Okay? Okay, and then like any other function, I have just curly braces. Okay, and then I have a close parentheses to close it for my thread here. Just going to be some function here. Okay, so what am I going to do inside of this function here? In the thread assigner, well, I'll just assign the value to something new, 42. I'll update that the value has changed, so I just have some boolean here. And I'm just going to print out what's going on just so you can see. So running thread assigner first, okay? And then I'll put a little end line here. Okay, and now that I've done this, I also want to notice or notify our conditional variable, okay, that something has happened. So we have notify and once, one time here, okay? Okay, so this means that we want to report the change has happened, okay? So we're going to create our other thread here, and we're going to create it first, but it's not going to, and it's going to execute first, but it's not going to proceed forward until that condition is true. Okay, so same setup here. This is a lambda function, so that's a parameter. We're just embedding it right inside rather than providing a address to a function. And then we're going to go ahead and let's just create a lock here, unique lock here. And it's going to be a mutex. Okay. And it needs a name. So I'm just going to call it lock and then M. Okay, what is M here? Well, let me just give it a better name, global lock. Okay, so let's go ahead and create our mutex up here. And I'll explain a little bit what's going on here as well. Global mutex. Okay, and then we will have a loop here that says, while we haven't been notified, and while this condition is false, our conditional variable, or rather our global conditional variable, that's what we've named it, global conditional variable, is going to wait on our global lock. Okay, and then when we're done with this, so if we have been notified and this condition is not true, then we'll print out what the value is. Print the value as whatever the value is. Okay, and end line. Okay, so let me walk us through this again, because the logic's a little bit wonky here. And if I indent this a little bit more, you'll be able to see the flow here. Okay, so what's going on here with conditional variables? Again, this isn't a course on concurrency, but I just want to show you that it's available in C++. You can use it, and you can do pretty powerful things with it, okay? So again, the idea of this program is we just have some value here that we want to change in a thread. And whenever it's changed, we want to notify or print out that that value has changed. Maybe it's something important. You know, you can think of an airline system where a ticket's been booked, for example, and you want some action to occur. So both of these threads are going to launch. This thread's going to launch. This thread's going to launch. And we want our program to make sure that both of them launch. So we're going to have our reporter join with the main thread, and our assigner also join with the main thread. The assigner's job is to just change the value to 42, change the flag to true, and then we call on our conditional variable, we notify it that something new has happened, okay? All right, so what's going on in this reporter? Well, again, we have the lambda function here, which I could take this code here, copy and paste it, put it up here and give it a name, but the lambda otherwise is just super convenient to just create these little quick functions and embed them when we launch this thread here. Okay, so what I'm doing here is I'm creating a lock here, and it's associated with this global lock. So it's got the unique lock in it, which is a little bit different than a mutex, meaning it can only be held once here, okay? And then while we haven't been notified, so while this remains false, we are going to wait here, okay? and we're waiting forever until this lock can be obtained, okay? And once we're notified, we wait and say, okay, are we able to obtain this lock? Well, by default, when we create this lock, it's open, okay? So we wait on some condition, obtain a lock, if it's available, which it is, we just created it here, and then we proceed forward, okay? And then when this lock goes out of scope, it'll actually unlock for us. That's with the unique lock, so then we can print the value. Okay, so let's go ahead and just try to run this and see if any mistakes were made, and then we will proceed forward. Oops, looks like maybe conditional variable. Let's see, condition variable is the proper type. So we're gonna have to fix this as well. But if you search for it, it is a condition variables is what they're referred to. Okay, and then I have, my global mutex. This is just called global mutex. Okay, and that's a better name for it. So this is exactly what it is. And we can just compile that. And let's see what else. And oops, one little typo here. This unique lock that we're creating here is created on the global mutex, but it's actually just a lock here that we're waiting on. Okay, so let's try that. That is good to go. And then if you run this program, it's always going to run the thread assigner first, and then it will print the value as 42. So it's a little bit of a weird program in how it's running here. But conditional variables, anytime you need to have or enforce some sort of ordering, again, you can think back to the concurrency example with a coffee machine, where maybe you only have one person accessing something. You can just do that with a lock, but maybe you need some event to happen or to update the state of something. That's where conditional variable comes into play. So again, those are available in C++ for us. All right, so here is the promise and future example again. Again, you can remember this with the analogy of your friend. At this point here at line 24, you loan them something, they go asynchronously, go do some task, start doing the computation here, and then at line 26 is when you say, well, I really need that result, so we've either got to retrieve it right away, hopefully you've already completed it or partially completed it, or otherwise we'll just wait here forever until we get that result here. Okay, nice explanation here as well. All right, so, and that last example is really a nice example if we sort of wrap things up from where we started of what we call blocking input-output, which remember is one of the big problems. If I go all the way back to, why are we bothering with all this stuff? Well, it's this idea that it's really hard. We can process things fast, but when we have to go to memory, it takes a really long time for us to retrieve data back. So this asynchronous stuff here is really the key when we can do something here, right? Maybe part of this computation in another thread somewhere else and make as much progress as possible in our program. Okay, then we say it's sort of less blocked. Okay, so here's the idea of blocking I/O. Another video if you want to check that out. Okay. So again, when to use threads, we're going to be doing a little bit more, heavy computation just to sort of exercise it. And you can see, the performance gain. And then there are threads for your GPU on your graphics card for graphics tasks. And then we've been using CPU ones. So Depending on the task, if it's very graphicsy, like we've been doing a lot of things with pixels, your GPUs actually have hundreds or thousands of threads on them, which you can speed up your programs, which is super, super cool. All right, so anyway, there's a lot further we can go into threads. I think this is super exciting stuff. Here's some of the tutorials and a nice YouTube series on it. But that's where I want to end us for today, and then we'll be able to get some practice in one of our next assignments. Okay, and then as always, don't forget to do your in-class activities.